All right, so we're going to talk about beam design. We'll hit one video. We'll do stress, axial stress, strain. Probably the next video we'll do a factor of safety, the bending stress, shear stress, beam up to beam selection, and then we'll run through a whole example in a third video of beam selection, deflection, and then any calculations and redesign, evaluation and redesign that we have to do. All right, so part 1 of 3. So if we're designing a beam, we want to make sure it can safely support the design loads that it's intended for. So we're going to look at 3 things. The bending, it has to be designed for bending, it has to be designed for shear, and it has to be designed for the deflection. We need to make sure it doesn't deflect too much. Every beam will deflect. We have certain limits on that, though. We want to do that with the least amount of material possible. So we want just the beam just large enough to meet the criteria we need to meet, because more material means more cost. We want to keep the costs down. All right, so in the previous sections, we've already established the design loads. We've already analyzed the beams for the shear forces and the maximum moments. Now we want to actually select the preliminary member. We're going to evaluate that design and make sure the information about it meets the specs that we need it to meet, and then redesign it if necessary, as to make sure it's safe and efficient. All right, so first things first, we need to talk about stress. So we're talking about stress, we're talking about the amount of internal forces acting between the particles of that member because of external forces that are acting on it. When we think of stress, kind of like we think of pressure, which is force over area. All right, so axial stress specifically is happening along an axis of a material, usually represented by a Greek letter sigma, lowercase sigma over here. Still force over area. We have applied force, and we're looking at the cross-sectional area resisting that load. So here's an example. Let's say I want to find the tensile strength of a 2-inch by 3-inch tension member that's subjected to a 45 kip axial load. Now, a kip is 1,000 pounds, so it's 45,000 pounds axial load. So force divided by area, we got 45 kips. Area would be 2 inches times 3 inches, or 6 square inches. That would give us 7.5 kips per square inch, or 7,500 pounds per square inch. So force divided by area. Now, if you have a stress on a material, that's going to cause it to have a strain. Now, the strain, we're looking at how much the material actually changes in size or changes in shape because of those external forces. We look at it as a proportion of its overall length, because the longer material, the longer it would stretch. We usually use a Greek letter epsilon to represent the strain, and we look at the change in length, delta L, over the original length. So this is going to be unitless when it comes out in the end, or you can think of it as inches per inch if you really wanted to. So for example, let's calculate the strain if we have a 16-foot long structural member that elongates 1.5 inches when you have a tensile load of 67 kips, or 67,000 pounds. So when we have that much stress on it, that much force on it, I should say, the strain, again, change in length over the original length. We have 1.5 inches over the 16 feet, but we need to make these units match. So we got to convert that 16 feet to inches, so times 12 inches per foot. When we calculate that out, we're going to get a pretty small number when we're dealing with steel, fairly rigid structures of 0.0078. That means for every inch of material, it's going to stretch just under 8 thousandths of an inch. Now, in many materials, the stress is directly related to the strain, but up to a certain point. So right in the very beginning here, it's fairly linear in the beginning. So as you add more stress, more force, it's going to cause a larger strain, like a rubber band. Up to a point, though, you have a certain place right here as a yield stress, where it's not going to be proportional anymore, and you're going to have some deformation. You'll get up to an ultimate stress with the highest amount of force the stress it can handle, and eventually it will fracture. So typically stress strain curves look something similar to this. The slope of this graph right in the very beginning, that's our modulus of elasticity. Basically, how elastic is that material? Is that really that stress over the strain? So in the very beginning, that linear portion we call elastic behavior. The material is going to return to its original shape. It'll stretch a bit, but it'll always come back to where it is. Once you reach the yield point and go past it, now it's going to behave plastically. It's going to be exhibiting plastic behavior. The material is going to retain some deformation when unloaded. So even though you take the forces off, it'll never go back to its original length. Structural members are designed to act elastically during the service life of the building. We want to keep all of our joists, all of our rafters, everything we're using, keep in that elastic region. We don't want any lasting deformation over the lifespan of the building. And also, we would need to build in some safety factors, and this will tie us in, segue us to the next video where we start talking about how we decide on how much of a safety factor, because we don't want to load it to excess. We don't want a beam sitting at that yield stress point, but how close are we going to get? And there's some codes that'll tell us how close to get that.